Okay, so that previous example was just two different unmatched samples. They were two independent samples. There was no reasonable way to match amount of time with the basic cable channel to extended cable channel based on the way that data was collected. So we want to also talk about how we can do bootstrapping for matched pair examples. So we'll take a look at an example in a second. But now we're going to have one sample that has size n, and for each n of those values, we have a second sample where there's a very natural way to pair those values. And so we're going to take our n pairs, and for each pair, we calculate a difference. And then we're going to do the bootstrapping from the differences. So then we're going to calculate the mean of the differences, record that value, and then repeat it again. So let's take a look at an actual data set, and that might help clarify this process. And we're going to re-investigate the example with the wetsuits that we looked at when we did permutation tests. So this was the case where they came out with a new wetsuit that some swimmers wanted to use in the Olympics, and they were curious to see whether that wetsuit gave an unfair advantage. And so what's being recorded in each of these values is, here's a swimmer. They swam wearing the new fancy wetsuit, and their maximum velocity with that wetsuit was 1.57. And then they swam again, and they didn't wear a wetsuit. They were wearing just a regular bathing suit, and this was their maximum swim time. So this swimmer had a difference in maximum velocities of 0.08 meters per second, this is. So they swam a little faster with the wetsuit. And they did this with a total of 12 different people. And in case you're curious, they randomized for each swimmer whether they swam first with the wetsuit or they swam first with like a regular bathing suit. So there was no fatigue that should have caused any confounding in this. So what bootstrapping would look like here, I've got 12 matched pairs. For each of the matched pairs, I have differences. And so now I'm going to create a bootstrap sample of the differences. So one possibility could be that I get 0.1, and then I get 0.1, and then I get 0.11, and then I get 0.05, and then I get 0.08, 0.08 again, 0.1, and I should do this repeating until I have a total of 12 values. So I think I'm definitely short here. So we keep on going. Well, that's a good one. Let's say we get 0.08, 0.1, 0.05, 0.06, 0.1. I think that might be 12. So let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, perfect, 12. So this would be a possible bootstrap sample for this matched pair. Okay, so now we're not randomly picking individual swimsuit times. What we're picking randomly with replacement are differences for those pairs. Okay, home stretch now. So last example, so let's now say we want to come up with a 95% bootstrap confidence interval to estimate the difference in the mean maximum velocities when you're wearing a wetsuit compared to not, okay? And now we're making this about an estimate for all people who would wear this new swimsuit. So let's see. Let's first take a look at the R code behind door number 1 over here. And what I haven't specified here is this wetsuit is a vector which has already been defined by the 12 wetsuit velocities. And this none is a vector that we've already defined using the 12 no wetsuit values. So those are just two vectors of 12 values, and they're ordered accordingly. And again, if you're curious, the full code is in this R file here, matched pair boot swimsuit. Observed is going to be the mean difference that we get from our original samples. So in other words, we're going to take all of the differences and then calculate the mean of those differences. N is going to denote the length of this vector difference. Okay, so this vector difference is in fact like the bottom row of that table that we were looking at before when we were illustrating what one possible bootstrap would look like. So N here is 12, right? So that should tell us that there were 12 values in this vector, but we'll just refer to it as this variable N. Capital N is how many bootstrap resamples we're going to do. So here we'll do 10 to the 5th, and we're going to store each of our results along the way in this variable called boot.diff. And then we run this for loop. And so what this for loop should look very familiar is we have this original sample of differences. We're going to pick n values, so that's going to be 12. So we're going to pick randomly 12 values from difference, where each time we pick a value, we're going to put it back and replace it before we pick the next value. Once I've picked my 12 values, I've got them in result, I'm going to calculate the mean of that, and that's going to be stored in boot diff, and we do this 100,000 times. And then using all of those differences that we calculate, I'm going to calculate the 2.5 percentile for the lower estimate and the 97.5 percentile for the upper estimate. And then again, I can make a histogram. This is going to show all of the differences that, all of the differences that we observed. Here's going to be the original sample that we got, and these are going to be our two cutoffs for the upper and lower estimates. So let's see behind door number 2 what that looks like. And so now we've got our confidence interval that we can see down here. So what we could say in this case is there's a 95% chance that the interval from 0.066 to 0.089 meters per second contains the actual difference in velocities that the swimsuit gives an advantage over not wearing the swimsuit. And again, what's of significance here is that this interval contains only positive values. So here we get an idea of what would be plausible values for this difference, and this gives me a pretty good, strong indication that that wetsuit was actually causing people to swim faster compared to their times when they were not wearing the new wetsuit.